Thank you, everyone, for coming to join us today. We're, of course, thrilled to have Dr. Yi-Hsin Liu here with us, visiting from Dartmouth. My name is Jason Schuster, one of the research assistant professors here at UNH. Happy to introduce our speaker. Yi-Hsin's graduate work actually goes back to the University of Maryland, working with Jim Drake's group and some of the state-of-the-art simulation work there, which he's going to be showing some of these simulation results in his talk here as well. And then after that, a postdoc at Los Alamos, also working with some of the state-of-the-art simulation researchers in our field, Bill Doughton and the team there. And then after that, an NPP at NASA Goddard, working with Michael Hesse, again, covering the whole trifecta of simulation experts and gaining expertise all along the way. So yeah, very exciting. And then of course, then once joining Dartmouth, Yi-Hsin has been there for several years now and is now at the associate professor rank with a long teaching record as well. So teaching and research as well. And my memories of Yi-Hsin go way back. Even when I spent some time at Goddard, Yi-Hsin was kind enough to give me the tour of the area and introduce me to everything. So I greatly appreciated that, and we're certainly happy to have him here. So with that, Yi-Hsin.
Okay, thank you. So do you mind me just sit here and using the cursor?
Yes.
Okay. Yeah. Very informal, right? Very informal. Okay. Yeah. So I'm Yi-Hsin Liu. From you who does not know me. This is how my Chinese name look like. Doesn't really matter. Okay, so I'm going to talk about asymmetry along the magnetic reconnection exercise. So this will be a longer exercise. So will be a 3D physics, 3D reconnection nature. And so here will be the outline of reconnection of my talk. So first of all, we'll talk about a solution to a fast reconnection rate problem. That's one. I'm going to spend only 3 slides on it because it's not the focus of this topic. And some of the people already heard it 1,000 times. So, and then I'll start to switch to 3D physics. We identified that using 3D peak simulation is a kinetic simulation. And reconnection is just like here, the figure. So it's involved the reconfiguration of the magnetic field line. And once like a blue line connect with the red line, then become like this, right? And in the magnetic field in plasma is spatial force called tension force. You see here become high curvature, so we shoot out plasma, and this will become a very efficient energy conversion mechanism. And so the focus goes on the first topic. So here is a famous chain reconnection challenge paper where people try to identify what's enabling fast reconnection. Okay, and we know you have heard of Sweet-Parker reconnection and then Pecha reconnection, but turns out Pecha reconnection is not self-consistent. It's why we have this chain reconnection challenge paper published in 2001. And here in this paper, they have this figure that showing the reconnection rate as a function of time. Therefore, the slope will indicate will be reconnection rate. It's how fast the flux being reconnected. You can see this 4 model, the comparison. Only this model actually with uniform resistivity show a slow reconnection rate. The other 3 have fast reconnection. Then people then look into the Ohm's law in plasma. It look like this. So it's E plus VI cross B. If this is 0, if right hand side is 0, is a frozen condition for the ion. But in the resistive NHD, we do have this term, resistivity term. And this can break forcing condition that enable reconnection to occur. And you have other terms in kinetic plasma. We have Halton and the pressure and the inertia. And by comparing this Ohm's law in the 4 different models, we realize that maybe this term is making a difference because when you have the Halton, the 3, then you have fast rate, and the value is roughly always like a universal value, 0.1. And if the simulation does not have the Halton like this, then it's slow. Okay, so from this paper, they conclude, and it seems to be very reasonable, that Halton is making the reconnection fast. But even though this result being published in 2001, for 20 years, people doesn't have a real good explanation of why this is happening. So now it's 1 slide, and I'm going to use this 1 slide to convince you why the Halton is giving you fast reconnection, just this one. Okay, so here is a reconnection geometry is inflow region have B field bend in this way, and you have outflow identical, okay? Because it turned out that what's really determining the rate is the upstream force balance, as I will tell you. And reconnection occur by definition is drawing in plasma from the upstream. Let's consider simplest case, cold plasma, low beta plasma. So once plasma get in, okay, you tend to deplete the pressure at the X9, okay, and then jet out on two sides. And in order to have a force balance across in the current sheet, you do have, if it's a uniform current sheet, it means that the pressure need to be as high as the upstream magnetic pressure, so indicated by this red area. But what I'm showing in this figure is that once reconnection start, it's unavoidable. This upstream cold plasma tend to deplete the pressure at the center. And that is important consequence, okay? Because if the pressure is low here, then the upstream pressure will improve into this diffusion region, X9, then we'll open out the exhaust. And this is basically the mechanism we are looking for to realize fast reconnection. And how does this relate to Houghton is this. So it's because now we need to ask ourselves, what if the plasma can be heated up, right? Then this is a question that we really want to answer. So look at in this picture, we indicate that the cold plasma cannot be heated up while it's being convected into the X9. And I'm going to tell you that Houghton actually is making this happen because the energy conversion from upstream magnetic field to the plasma is J dot E. Everyone here know about this, right? It's point in theory. And inside the IDR, you know, ion diffusion region where ion already demagnetized, but the electron is still frozen in. Then the electric field is dominated by the whole electric field, which is J cross B. In the Ohm's law, you can see here is J cross B, as I just described. So then the energy conversions will become J dot E whole, and will be J dot E whole, J dot J cross B, and all of you here know that this will be 0. It's a vector identity, right? So this indicates that because of the whole electric field, the energy will not go to plasma within the IDR, but outside the EDR. And this is limiting the energy conversion to a plasma. So then imagine you have a cold plasma get in. It might be heated up or might not, but in a collisionless ion proton plasma, because of the Hall effect, it will not be heated up very much. And this will become colder. Once the pressure drop, this means that the pressure difference from here to here will be smaller than upstream magnetic pressure. Low pressure here, high pressure here, then will improve into the X9, locally pinch it. And then it will open up the outflow exhaust. And that will make the aspect ratio larger. If delta divided by L will become larger because of this reason. And therefore enable the fast reconnection. Any question on this? Just one slide explain this 20 years old puzzle.
And so this is just the region outside of the EDR, but inside the IDR.
Yeah.
The bidding, right? That's the
Right.
happen. Okay.
Yeah. Inside the EDR is what Kevin will emphasize, and you guys, you do have energy conversion. Yeah, but the energy budget is small. Yeah.
So if you think of NHD, where this doesn't happen, because you get extended
Right.
energy, couldn't this argument almost work there in the sense that if you imagine the inflow in NHD, you don't expect much heating before the material gets there?
But you will, because in the resistant energy, the E field, non-ideal field is eta times J. So eta, the J dot U become eta J squared. It's always positive. And we can do some estimation like we did in paper and show that, yeah, it more or less give you a pressure balance across in the current sheet. And that was actually being assumed in Sweet Parker solution. Just assume it's the system size long current sheet, right? But it's assumption. And he does not really show that will happen. And the pressure balance is one of the critical thing.
Is preface that when you have the Hall term, you have that thick ion diffusion region, and all the heating is in this tiny thing.
Yeah, there's a big energy difference. Many field energy being not being converted, being diverted to the outflow region. And a lot of energy is not being converted before the plasma reaches the X-line. Okay, Jimmy.
Well, it's like the Gen paper.
Yeah.
It says that, what you said, and Gen paper said, what people say, I mean, MHD does not produce fast reconnection, but that is plainly wrong.
Well, this
There
is a
is
unit
a
with,
paper,
yeah.
there's a paper right after that paper in the same journal, and written by Tony Startle, where he actually compares different MHD models, I mean, with localized resistivity and current dependent resistivity, and he finds that in those cases, you also get fast reconnection.
We know that. And what I say here, I mark it as a uniform
Well, it's-
resistivity.
it's-
Yeah.
He
Yeah.
also made the statement that you only get fast reconnection with a halter. I mean, you can get fast reconnection without.
Yeah, so yeah, this that's not totally, yeah, what I say is not totally correct. I agree with you. And in the paper, we do mention the case with anomalous resistivity. So there can be other localization mechanism. It's not always need to Halton. Like in the electron position plasma, there's no Halton, can still have fast reconnection. And we still can figure out what's causing that. So what I want to say is the different localization might operate in different systems. But here in electron proton plasma, we think Halton is the critical physics mechanism. Okay, yeah, we can discuss later. Okay. So, okay, and this is the simplest is take-home message for this. And actually, not many people know. I actually got this idea after Kevin Gymnastics talk at Dartmouth. Yeah, he also showed this J dot E is 0, and therefore then move on to the EDR. And that time, I think.
Biggest contribution.
So you are on this paper because of that, because since that time, I started to think more carefully about this fact. How can this actually lead to fast reconnection? So it's a good indicator that we do need to have a continued communication in a seminar, right? Exchange an idea. Well, and this is another way to look into this, and I'm going to spend the time on this. You already know the most important is that J dot E Hall is 0. It's the take-home message. This one just another way looking into this using pointing vector. Okay, you can see that in my paper. Now let's move out to the 2D physics. Now let's look into the 3D. In 2D, it's 2D, right? And the reconnection X9 base technically is infinitely long because there's translational invariant in the outer plane direction. But now let's look into the opposite limit, trying to make it short. And let's see what will happen. Okay, it turned out, and I'm going to show you that when the X9 is too short, you will be surprised. It's what you will see. And it's a peak simulation. And what you see here is the initial setup, okay? And you are looking at a ZY plane in a more or less like GSM coordinate. So it's not a reconnection plane, okay? It's a reconnecting field is like into and out of plane, this plane. So you are looking at the X-line direction is in the Y direction. It's a cross-tail direction. And so what do we do in this initial setup is we embedded a thin current sheet within a thicker current sheet so that we can control the total X9 length in our simulation. And the thick current sheet does do that because X9 will have a challenge spreading into the thicker current sheet. So in this way, we can confine the X9 length. And then because it's a current sheet, right? You need to have a current carrier. And the kinetic physics in kinetic plasma is very different from resisting HDs that we do need to have a particle to carry the current. So you put a current like this, pointing up, you have ion drifting upward and electron drifting downward. And this will give you a lot of symmetry I'm going to talk about for the rest of this talk. So it's the drifting speed is different, okay? So now let's get go. This is how it look like at the nonlinear stage. Ion drifting upward, electron drifting downward. You see that the X line become thinner and intenser, more intense in this side. So it's where electron drift into. Okay, I'm going to tell you why. And then this is the ZY plane again. And here this two plane is on the XY plane, will be more like in the equatorial plane of the tail. And you look at X and Y. And you can see that while this reconnection become nonlinear, it's more active on this side. So associated with this thin current sheet. And the explanation is that because is reconnection occurring and within a DI scale, we have the Hall effect. We still have Hall effect in 3D. And what Hall effect do is that means that electron is still frozen in the flux, many flux still frozen into an electron, therefore will be carried downward by the electron. That's why the reconnected B field, BZ, is being carried downward. Okay. Yeah, the color here is BZ, is a reconnected field, and the X line will be in between. Is okay? The geometry. Yeah, it takes some time to get familiar with the geometry I'm talking about. Yeah. Yeah, okay. So yeah, so reconnecting B field like this, right? In and out. So it's happening here. But now it's in this plane.
Okay,
Yeah.
yeah,
So sitting from the top, looking into a current.
but
It's opposite.
then your magnetic field, there looks more dipole than should be then.
We don't have dipole here. So we only have planar B field here, but it's just current sheet is different. That's the
And yeah, the dipole is the BZ, like, and one reconnecting out.
But, yeah, but I would expect to see a quadrupole there if there's a halter, right?
Only if you look at the X Z plane.
Yeah, if you
X
rotate it,
plane.
you see that.
But I didn't show the X Z plane. Yeah,
Okay.
that will be a typical reconnection plane we show.
BZ, the reconnecting field, yeah.
Reconnected field.
Reconnected field, yeah.
Yeah.
And if it was a typical 2D simulation, Jim,
Yeah,
that middle
so-
panel would be infinite in the vertical direction.
Like this. Geometry is like this.
Yeah.
Yeah.
Right.
So the typical reconnection plane, there will be X and Z. Throughout the talk is like this, okay?
Yeah.
The
it's like
B field is
that.
like this.
Oh.
Yeah, we rotate from cold factor.
So,
So that way,
but if it were in that plane, you would see. the
You will see
quadrupole.
what co-quadruple field.
Okay,
Yeah.
I'm sorry.
yeah.
We don't see this here. But actually, it's like a B field actually will be bending this way. You plot a contour. Now, if you trace the field line, you see the B field is like this.
Yeah.
Yeah. So the whole quadruple structure.
Yeah.
Okay, so in 3D, it manifests in this way. So it's basically a transport of BZ toward the electron drifting side. Okay, and later you can even have a secondary Turing mode. And why this is actually essential for making reconnection stronger is that because the BZ will is important to drive the outflow. It's either through the J cross B or you can look at tension. The tension here will need to have B field in the Z direction, normal direction. So this means you have a strong BZ, you have a stronger tension force, will drive outflow, make the X line in between healthier and thinner. Okay, more active. But on the other side, actually, because the BZ once reconnect, being transported downward, so you don't have a strong signature BZ here. It's being suppressed. So this 3D physics, intrinsic physics, tell you that one side of reconnection will be weaker, one side will be stronger, and it's has something to do with the transport of BZ along by the electron flow. Okay. And this one turned out to have some application. When I'm doing this study, I only want to do the fundamental physics and later trying looking for the application. And luckily, I realized that actually the entire system size is very similar to the Mercury, the tail of Mercury. So in the tail of Mercury, that will be like an entire cross tail length, okay? And in mercury, they do found there are more FTE event on the downside, which will be this side. It's where electron drift to. On the downside of the tail. And as this seems to be consistent with what they observe, that means by messenger, and hopefully by baby Colombo later. Any question on this? No? Okay, and then now let's look into the detail. So still it's in the ZY plane, okay? Reconnecting B field is into and out. And we plot the non-ideal H field, and it's brighter here, indicate a stronger reconnection rate, and weaker here means it's suppressed. And then take a cut along this line, just focus on this the red line, small, indicates being suppressed, and larger here. And it's similarly large as 2D simulation is 0.1. And the outer turn inside the outer turn in the Ohm's law, the breaker forcing condition. Okay, and now this is the typical structure asymmetry seen in the X-line of finite length. Now let's ask a question: what if we make it much shorter? Okay, and when it's much shorter, means that the length here, it can be as short as this, right? Make it short like this. This means that the magnetic field, once being reconnected, the BC will transport to the other end right away. So this means that when it's too short, most region will be suppressed. The entire extension is being suppressed. When it's large, that's fine, it's like this. Certain region down here is reconnecting, but it's too short, it will be suppressed. And this is what we see here. So in this is 2D case, the reconnection rate is function of time. And this is long enough, rate order 0.1. When it is low, when this system, the length here is short enough, like it's below 10 di, it start to be suppressed. So it's far away.
Do you change the simulation box size? Or?
Yeah, box size.
Yeah.
You can change the entire box size or just make the thin current sheet become shorter.
Do you resolve the current sheet across?
Across where?
Across the current sheet, do you have the resolution to describe its structure?
Yeah, we do. Yeah.
Is there like an election structure inside there in addition to an ion structure, or is
They are.
Is it
So something like this. This is the EDR scale.
this
Yeah,
is the
sure.
ion scale?
This is like ion scale.
Yeah.
Yeah.
Is there an electron scale? Inside?
Yeah, electron scale is also resolved.
Okay.
Yeah, this is a requirement for study for the kinetic reconnection, the peak
Is there a
connection.
structure on the electron scale? Sub sheet or
It really depends on the parameter, but for this round, you can see it's pretty laminar. Yeah, don't have like double ray or other kind of instability going on there. Okay, so I don't remember the detail. It's roughly, I think it's maybe 75 for this case. Yeah. Yeah, well, yeah, exactly. For 3D reconnection, you cannot do a full mass ratio. Yeah.
If you couldn't put the 6 on the scale that you see.
You can, but it will be super expensive.
Well, no, I mean, on your figure.
Yeah.
Yeah, right,
It's so
right.
much smaller compared
Right.
to
True.
Maybe you talk about it later, but I'm trying to think of how, so the argument for reconnection happening, so here you're saying it's the ion coupling to the reconnection that's giving you the minimum length of an X line
Yeah.
in the current direction. But the people are saying if you have a current sheet that's too small for ion coupling, then you can get reconnection just proceeding only with
With the
electron.
electron, right? Yeah.
But I guess the difference there is here you have a current sheet that's sufficiently, or your system size is sufficiently large in the outflow direction
Yeah.
So ion should still be
So-
able to exhaust.
Yeah, I will argue that what we're looking at is we're trying to look at reconnection that can reach a steady state.
Mm.
Okay, ion eventually will couple.
Ion eventually.
Although it's like a Poirier fluid, okay, there's actually only 3D reconnection. I think it's very transient. It happened, yeah, but quickly we're run into the boundary already.
Okay,
Yeah, it's what I think. Yeah. But if you want to look at, you want to have a steady state, then 10 DI for this separation region probably is required.
okay.
And this 10 DI well can be estimated just a nonlinear time scale, a time scale for reconnection to let go to fast reconnection times the drift in velocity. And this can give you roughly 10 DI.
So just to make sure I understand, you're saying that reconnection could occur localized within that, a scale of that suppressed region,
Yeah.
but it would have to be transient. It could reach a steady state.
So it probably can start at a very early time, have fast burst of reconnection due to electron only reconnection, but this will drift downward
Okay,
and then run into the wall, disappear.
gotcha.
Yeah, this is what I would expect.
Thanks.
Okay. Okay, so this seems to be a reasonable explanation for the, it is one of the possible explanation for the down dust asymmetry for the mercury. Downside have more signature, dark side has less signature. Okay, how about in the Earth? So in the Earth, turn out that down dust asymmetry is opposite to mercury. It's what people say, okay? And here we're trying to explain why. And it turned out that it's like the scale size making a difference. And here will be the argument. So go back to the mercury case. It's a short case, right? It's a short total cross tail extent. And this is our simulation. And now the planet is on the left-hand side. So let's switch it like this. So the downside will be on the top and the dark side will be in the bottom. So this will be active region like here, suppressed region here. So indeed, in downside for mercury is more active. And remember the argument used to make this is that the transport of the BZ, you see here, the BZ is actually the how dense this field line across the midplane. Here is BZ is stronger compared to here because it's being transported by electron to here. Okay, and in the tail, in the Earth tail is larger cross tail with larger cross tail extent. And before the onset of reconnection, you also have BZ, like, because we have actually you can start from a tail geometry that have this initial BZ associated with it. So this, when you try to thin down, it also being transported upward here in this figure to the downside. To make here the BZ stronger compared to on the dark side. And this actually have another thing that will compete to determine the location of reconnection is the onset location. And this have stronger BZ. It's harder to onset for reconnection onset. Here have a weaker BZ from the tail geometry. We have better chance to onset. So the picture we propose is that this happening, okay? BZ before its form X line is being transferred to this direction. It's not our idea. It's like a Sanlu's idea. Sanlu from UCLA. And then reconnection try to onset here. And once the onset, this internal X-line asymmetry we're talking about does develop, but it's only locally effective in the downside. So if you are an observer, okay, you'll conclude for the Earth middle tail, you'll conclude that most events still on the dark side. And here it's being suppressed. Maybe it's indicated it's correspond to this suppression. Yeah. And this is a paper from Tony, yeah, ideal and the thin current sheet distribution. So maybe this is an explanation for this down dust symmetry in Earth versus in Mercury. Any question on this? Yeah.
I mean, you can put up a lot of other hypotheses, I mean, why you have an asymmetry like that, you know, I mean, one would be, I mean, the differential orientation of the INF, I mean.
Yeah, there are certainly
Another
other mechanisms.
one would be, I mean, feedback from the ionosphere, I mean, or the drifts, I mean,
Right.
in the magnetosphere, you know, in the ring current. So have you tried, or anybody tried, I mean, to falsify any of these hypotheses? Because otherwise you don't make any progress.
Exactly. So they are competing mechanisms and can be writing as a book, review book. And here we just propose one mechanism based on simple reconnection physics and current sheet physics. Yeah, and I was not able to verify this because I'm doing peak simulation only. Yeah, but maybe in the future, a more realistic simulation have both the global physics and the kinetic physics, current sheet physics, maybe we'll be able to resolve it.
Is there new data from the global or something?
Yeah, I've been trying to ask him, my collaborator. I think they didn't get the stage of showing the B field structure yet. Maybe still don't have enough or still calibrate. I don't know. Yeah. Okay. Oh yeah. So and also from this argument, you know that the global extension of a tail does play an important role in determining which asymmetry will be revealed. Now let's move on to the third topic, the X-line spreading. So unlike our previous setup, now we have the current sheet that's uniformly thin DI scale, or maybe 2 DI scale in the Y direction, okay? B field is still, reconnecting B field is still into an outer plane. Okay, and the difference is then we don't have, it's not embedded in a thick current sheet on two sides. So, and it's much larger. It's like a 200 DI, more than 200 DI now. And what we do is then we trigger reconnection right at the center at time 0, and then let the reconnection signature propagate out. So the reconnection will have freedom to propagate in both directions in certain speed. And that's what we are trying to study. So the spreading problem. And this will be one of the result. So this is a result without a kink instability. Okay, and here you're looking at this equatorial plane XY again. It's at time 40, it's early, and the initial perturbation is like this long. So X-line will start right away with this length. And what you are seeing, the arrow is electron flow. And the color here is BZ, the reconnected field again. In between this blue and red will be X-line as before. At later time, you can see that this become more developed, the reconnection X-line. And I want to emphasize that we do see the similar asymmetry discussed in the previous topic. The flux being transported downward along with the electron due to the 3D Hall effect. And we also see that the X-line itself trying to extend darkward to the which will be along with the ion in this set of simulation. At later time, look like this, okay? Fully glow outflow. And yeah. And I'm going to show you that I'm going to discuss what's causing the spreading of this X-line, especially in the ion direction. And before we do this, let's look in the movie. It's how it look like. So the panel here show the ion velocity on the equatorial plane. Yeah. And the X-line is in between. So you see the development of the outflow. And the ion is dripping upward, so it's in this direction when outflow develop. And for electron dripping downward, is like this. You see inside the IDR, the electron velocity does become very strong, but it's not causing the X-line to spreading down in the downward. Only ion is causing the spreading in this case. Okay, And for this, then I'm going to tell you without further evidence, more detailed analysis in the paper of my student. We conclude that maybe this is the temperature, the low temperature, the low pressure at X9 is drifting along with ion to the upwardly in this figure, and this will lead in the continual onset of reconnection. And this connect well to our first topic. The whole turn cause fast reconnection because the pressure depletion. Here to tell you that in 3D, initially you have X9 happening here, is enabled by the lower pressure. And this lower pressure is mostly in the ion pressure, and they will drift upward. Once it drifts upward, will cause the collapsing of current sheet locally in the edge, and that will cause a continual onset of reconnection, and therefore the spreading of X9 in this direction.
Just, is your initial current, are your initial conditions, your initial current sheet configuration,
Yeah,
is that translationally symmetric along Y?
yeah, it's
So
usually
it's the same initial thickness all the way. up.
right.
Could you show the current sheet in these pictures? Where is the current sheet?
Yeah, so you are actually looking entire current sheet right now.
Yeah.
So you are looking at this plane. This plane, 2D plane going out from the
So
top.
it's a cut of the
Yeah.
current sheet.
Yeah, top
Z equals 0, maybe.
along the spatial current sheet.
No,
It's
it's in the plane.
It's in the plane, yeah.
The current is in the plane.
Yeah.
That's right.
So initial current density is the same over the entire plane. It's a peak value.
Okay, so the X-line initially spreads, but then the spread stops. Okay, I mean, that's the way I see it.
Yeah, I mean, that's right.
So, I mean, it goes to a certain point and that's it.
Yeah.
Now, what limits that? Why?
So we
stop?
think that, yeah, we don't want to see it stop, but however, it still stop. And we think it because the boundary condition acts.
Correct.
Okay, so you go in here and coming back to affect
Well, what there
the
is, at least
spreading.
the Earth's tail, there's actually evidence that the bursty bulk flows, you know, that they, I mean, that's basically what you showed there.
Yeah,
That they are limited in width. I mean, there's papers for Rumi Nakamura and, you know, 20 something years ago, that typically they're between 1 and 3 RE or something like that.
Right,
You know,
yeah.
They don't go further, you know, they don't spread further. So
Yeah, maybe
the
it's-
question, what limits that, you know, I mean, it's, you wouldn't assume that it's an MHD process, but surprisingly, I mean, I'm doing global simulations, MHD simulations, you know. We see the same thing. They don't spread forever.
well, but in
They
HD,
definitely do not spread.
yeah,
Like you see it in a lot of cartoons, you know, across the entire tail, and virtually never happens, you know, I mean, you always get these channels, and you get multiple channels at the same time. So, I mean, for me, it's still a mystery, I mean, what limits that?
yeah, okay, so,
Something you-
ideally, if we have a very large system, I expect we will continue to spread,
Yeah.
okay? And, however, since it's probably very sensitive to the boundary condition, the boundary at the X direction.
Oh, yeah, sure, sure.
Yeah, but in NHD simulation, I don't know what's the mechanism that cause the spray. Because there's no current carrier that we are being discussing that can cause the spreading.
Well, I mean, it can be other reasons. I mean, you have a finite thickness of the current sheet, so actually the width of the reconnection channels, I mean, sort of correlates, I mean, with the width, with the thickness of the current sheet. I mean, that's one thing. The other thing is, in reality, it is not an initial value problem. I mean, the way you set that up never happens in nature. I mean, you never have a current
Yeah.
sheet that is undisrupted and just sitting there and waiting to reconnect, you know, that doesn't
Sure,
happen.
yeah, yeah,
I mean, it's a continuous process. There's always a new reconnection happens. Old reconnection has already been there and has already created.
Yeah.
values, you know,
It's a
which
fully
of course affects
complicated,
the new
yeah,
reconnection.
true.
I'd like to think of maybe the answer at global fluid. As a finite width.
Talking about your old paper with the.
Yeah, so
No, it could be, I mean, it could be a feedback mechanism with the ionosphere as well, you know, I mean, either through outflow, but also through field like Earth, for example.
Yeah.
So, I mean, there are these wedgelets, although I would think that the wedgelets are actually a consequence of the finite width of the reconnection
Yeah.
outflows, you know,
Yeah.
not the pores, you know, I mean, you cannot really prove that.
yeah, so I would say until we are really able to solve the multi-scale problem in a single simulation, I think no one will be able to. Yeah. So this just tell you that if the kinetic physics dominate, will look like this. Yeah.
One more question too. So you're talking about how the interaction between your jets and the boundaries in the outflow direction
Yeah.
might be limiting the spread. I wonder also about how the inflow conditions are changing as a function of time.
Oh yeah,
Like,
that's
I wonder
another
if you're
thing.
running up against depleting
You can, yeah,
it
it's
low
possible.
analog.
Yep. Yeah, it's
There's
possible.
really an energy budget argument that
Right.
limits the spread to you'd run out of if you start reconnecting in tail faster than you're supplying open flux from the day side with some huge X line taking up the tail, that's just not sustainable.
Oh, sure, of
Yeah.
course. you know,
Yeah, we'll
I mean,
shut off at
That's
some
not
point.
really the question. I mean, you could still have an excellent that goes all across the tail, you know, in which that sort of dies away. I mean, because there's no more flux to reconnect, you know, but that's not really what you see. I mean, neither in the data nor in the simulations, you know, you see these channels, you see episodes of intense reconnection on a channel that is only a few area wide, you know, and then eventually it dies away, you know,
Yeah.
where it moves, you know, it moves actually tail. And then the new reconnection points, or little X lights appear. you know.
Yeah.
And so at any given time, I mean, in the simulation, I can see, I don't know, 10 or so X lights at the same time. You know,
Well,
and
another
I believe
mechanism.
The LFM people or the Gamera people see even more. And
Yeah.
now we don't have the observational capabilities to actually prove that. You would need a constellation of satellites.
That's why we need wage for this, right?
Or links to.
No links.
Which we have been talking about for 30 years. Right?
Yeah, so we need to get it.
40 years, 40.
Well, yeah, maybe like a balloon entire interchange instability will make it narrow flow channel as well. So multiple global physics can be. Yep.
In my. So,
Okay, so I still have time. So this is the case without kink instability, and now we can actually bring back the kink instability. And now this is a case that actually allowed it to kink. I didn't tell you how I suppress reconnect kink instability on this other people ask, but so far just say we have a case where it's basically a companion case of a previous case, but now you see this kink structure on this equatorial plane. Okay, so we won't do this because we want to say what the kink will do to the spreading. And you can see similar evolution. Kink become unstable on the ZY plane. Initially, you have a cast develop similar to the before, but later disintegrated. So this indicates this fluctuation from the kink actually is stopping the spreading of X9. And detail mechanism is hard to really pin down, but at least you see the current sheet become thicker because of overflapping. So right now we just stay with this argument that maybe it become too thick, so it cannot go down to the kinetic scale to have a healthy connection. Okay. And this is one example of the fluctuation or turbulence itself does not cause the onset of fast reconnection. Some people will argue turbulence can do this. I mean, but here is an example that does not do it. Any questions so far before I move on to here's the evolution. See disintegrate at later time. Okay, now the last topic. Not sure whether I have time. Okay, any question before that?
I wanted to ask about the distribution functions in your simulations.
Distribution,
You
particle.
look at the particle distribution functions. Is there anything peculiar happening
In a 3D?
looking around the reconnection site, like maybe an isotropy of the temperature
Oh,
that could potentially be used for, I don't know, maybe connection with the observation. Try to locate the site.
I would say, yeah, I think we should do it, but we didn't, and because we didn't,
But you do have all this information, right, in this.
not at least, not right now, all being purged.
Oh, I mean, in principle,
In principle, but yeah.
You would have all the,
Yeah. So yeah, if I have infinite amount of location and money, I will continue this project. But the next one will be saving the particle data for a similar round, and then I know where to save. You need to know that. You need to do the first round first, so you know where to save. Yeah, and then we'll take more location in this space. Okay, now this one is even more intriguing. Okay, so similar setup, uniform current sheet, but the shorter is a smaller box, but now have a guide field. And now we make the boundary condition on the two sides to be open, and therefore electron drifting downward will escape, ion drifting upward will escape. And this will also give you a chance for the X-line to develop a symmetry. If it is periodic, you're not going to see it, right? Because everything just come back, recycle back. But now you have the open boundary, it's possible to see the development of asymmetry along the X-line. Okay, if we just circle it back, you're not going to see it. That's the argument. So open boundary for particle and still drifting like this. Then now goes to this. Not sure we will have time, but let's try. So talk about the aura structure. So let's see this typical aura acceleration region. Okay, you have a tail, you have a generator region, and it will cause the shear flow, and the shear flow like here, V5. This will drag the dipole field and then making the B5, which is horizontal B field, into an outer plane. Originally, you have dipole field is only radial out. Now, because shear flow will generate less, will become clear in the next slide. And you have a B5 like this, you have the current sheet, right? Because the if an anti-parallel B field, you do have a current sheet. So this will be the J parallel. Okay? And if a J parallel is pointing up, means the electrons are precipitating down, and this will give you aura. It's the typical picture for the aura acceleration region. A spatial, and actually it's B here. And why it's called acceleration region? Because the same shear flow dragging effect will give you V5 cross B dipole, which is pointing inward in this between these two sides. And this for the electric potential, like integrate along this, will tend to be constant along the B field. Now it's brought up of this region to here. And therefore, this will indicate that at this region you need to have a E parallel, E field pointing up. So that the field line is basically the contour of the potential, electric potential. Get it? So say again, you have E parallel here from shear flow, and the lower side need to have this so they can stay equal potential on the field line. And this will be an aura acceleration region. You see electron precipitating down, see this E parallel pointing up will be further accelerated. That's a typical U-shaped potential. And now we are not the first one. Like Chaston is one of the people propose that maybe this, what we just say, indicate reconnection can occur, because the shear flow drag will cause this B field have a B shear in this direction. And if you take a cut in this 2D plane, you see the anti-parallel B field. Okay, you have these geometries right for reconnection, and once you reconnect, you can have an E parallel in the same direction needed for the U-shaped potential. So you have J parallel in the right direction, you have E parallel from reconnection in the right direction. So maybe it's a good ideal region for reconnection to occur at aurora acceleration region as well. Not just double layer, people have been arguing forever. Okay, so it's a new scenario. So then just based on this, then look, we do simulation, and this will be a 3D simulation I showed you before, and this will be the XZ plane at the bottom of this simulation, which indicate lower altitude side, closer to the ionosphere. So you see how it is. So you see the shear flow will generate B5, but in our simulation, we don't have shear flow. We only have B5 to start with and let it go. We have guide field as well. And how the reconnection look like. Here, what we plot here is J parallel. Okay, primary X9 and the secondary X9 along the separatrix, only one branch, because with guide field, only one branch of the separatrix will be, because we cause some asymmetry, and the one branch will become stronger, more intense, with more intense current. And I'm going to tell you that this might be a mechanism to explain the aurora spiral seen in aurora. And it's like this. This is a simulation, and this is what we are talking about. We think this is the aurora spiral that is maybe consistent with the flux roof structure in the guide field reconnection. Okay. Okay, then this 3D simulation as function of altitude. So it's along the B field at different cut in this simulation. So have a higher altitude at the back. Here is in the middle, and here will be the bottom closer to the ionosphere. And what I'm plotting here is a string line of the current density. You know, bit J is more or less 0 in the non-relativist limit. So it's convert the current continuation, right? You see this current center around this primary X line spread into this one branch of the separatrix, and then making tearing unstable. The secondary tearing become unstable on this branch, and causing this spiral structure. And there's some asymmetry seen here. X line is more or less so the primary X line is here, all the way crossing our system size. Yeah, it's from here to here is primary X line. But there's a symmetry occur, and it turn out in the lower side, which is lower altitude side, you have the tearing mode. So happen here, not in the back of the simulation.
But wickedly strong guide field, right?
Yeah, with strong guide field.
Yeah, okay.
Yeah.
I think I got it.
So then this is the asymmetry we're talking about, another kind of asymmetry. And this is because, so it's our argument that because this basically secondary tearing mode, right? And then for a second, you will understand the tearing mode is basically a resonant process of electron with the electron with the electromagnetic field. But you know electron is propagating downward. So what happens is initially it's like current like this and become tearing. So there's time of flight effect. It takes some time to develop at lower altitude.
Yeah.
That's what happened here.
You remember Antonius Otto talking about this kind of stuff?
Arnold, Dr. Arnold?
Antonius Otto.
Yeah, he has paper on this, and basically the same idea. But what he did that time is the NHD simulation, which does not show spiral structure, because it does, from what we understand, you do need to have kinetic physics to show this spiral structure.
Yes.
Yeah. And Sider, I think Sider is maybe one of the guys doing this kind of propose this idea as well.
And so then these spirals are basically like hugging the separatrix.
Yeah, having a longer separation.
And almost like a cage. There's a little rolling, but
Well, I'm going to tell you it's not KH.
oh, okay.
The rotational sense is the opposite.
Oh.
Yeah.
Hmm.
Okay, so then here's a simple cartoon mechanism. Okay, we have entire X9 happening across the Y direction, And the electron at the back of this box will be accelerated by the reconnection field. And while being accelerated, propagating downward, it will trace the field line because we have guide field, we'll trace the field line and go into one branch of the separatrix. Okay, and this intensifies the current density, J parallel. And then once J parallel is strong, it's more easier to have tearing. And tearing will just like give you the multiple X line. And tearing is just like a baby stage of reconnection. They have a similar look of its parents, so have also branch. This branch is intensified. And now you connect this, this means the electron will be further funnel into the O line in between and form this spiral structure. Okay? You like what?
Or how strong is the guide field?
So just strong field would- the thinking back then was that guide field really suppressed reconnection.
Oh.
Very strongly. You can talk to Katerina and the security,
Oh.
but she was working with him on that.
So from simulation, guide field does not suppress reconnection. Yeah, it is from peak simulation. The largest one we have is 100. It does not. You have still have a similar fast rate. Yeah, I know people say that guide field might. It does decrease a little bit, but does not. Yeah, change it a little bit, 2 or 3 times, or maybe make maximum 4 times difference in reconnection rate, but does not kill it. There. Yeah.
But you do see guide field suppressing reconnection.
Yeah, it's surprise. Yes, what people say, but it's not conclusive. Yeah. I know Yamada, they say that, but all other people, since there may be some chance they can suppress. But I would say let's make it open. From simulation, we don't see it's open, it's being suppressed. 2D simulation, simplest case. Yeah, maybe it's boundary effect can suppress it. I don't know. Yeah. Okay, so it's just embedded inside, but I would not say it's go away. Yeah, yeah, it's harder to see. Yeah. Okay, so here I tell you the one rotational sense, right, with a guide field pointing in this direction. Now, however, from observation, the aurora spiral, the rotational sense actually is opposite at north versus south. And what we are showing here is at the south, where the B field pointing to the ground. But in the north, what will happen? Oh no, sorry, it's in the north. So B field is pointing to the ground, into the ground. In the south, it's pointing out, will be like this. So in this case, then the field line connection become like this. So the electron instead of string along to intensify this branch, it will string along this red line, red B field, and intensify this branch and this branch. This means that all the baby will look opposite, and the spiral sense will become opposite. So what I say is that this mechanism, the punchline is that we can explain the rotational sense of spiral. Okay.
So
So-
that's the same thing that happens in the spirals you see in auroral images. It's flipped in the north and
Yeah.
north and south.
It is one explanation. It probably is only one explanation right now. Yeah. I don't know other work. Yeah. And also this, because I say this is the X-time asymmetry, right? So the current sheet will start to filament only at a only when we're at a low altitude direction. So this means that there is certain intrinsic length for the X-time to be long enough for the tearing to develop at a lower altitude. And we can estimate using this. So electron drifting speed divided by the time scale of the tearing mode, which is 1 over gamma, and then we get some this formula. Plug in a number, we get roughly 10 to 4 kilometer. This, when it's long enough, you see it's possible to see spiral. If it's too short, then you cannot see spiral because the current just goes down and does not have a chance to filament, okay, before hit the ionosphere. So and this is some study of the aurora acceleration length, aurora acceleration region length. Okay, some are longer than 10 to 4, some are shorter than 10 to 4. So we expect that the one longer than this can see spiral. The short one probably will not be able to see it. This is just our prediction. No observational study yet. Okay, that's a prediction. And here is just another example of a spiral observed from the ground, and the rotational sense is consistent. And maybe also happen in Jupiter as well. Like this certain region is called a swirling region, and this same mechanism, the reconnection happened at the here, roughly here. Oh yeah, aurora acceleration region was also being proposed by this guy. Similar mechanism, and now our kinetic simulation and our idea can explain it's possible to explain the swirling of the aurora signature, maybe in Jupiter as well. But it's not what my understanding is nobody have studied this yet. But so I hope someone will pick this up. Okay, so here, finally. So I tell you the whole effect to fast reconnection through this pressure depletion idea. And the spread of reconnection X9 is facilitated by the drift of low pressure plasma from the active region. This is what we see in our simulation. Then X9 asymmetry may explain the down dust asymmetry in Mercury's magnetite tail. And this revelation of it's basically a 3D Hall effect. And maybe combined with Saint-Louis picture, we can explain why the asymmetry is opposite to that of Earth. And now the last topic, the flux rope in the aurora acceleration may explain the rotational sense of spiral. And the rotational sense will be like this. It will be counterclockwise if you seen from along the magnetic field line. Okay, just this is working for the spiral. Consistent with the northern versus southern hemisphere, and it cannot be explained by Helmholtz instability. I'm going to tell you why. Because you see, here will be a local shear flow direction. So you should have a Helmholtz in this way, right? Right. Okay, you remember it? I'm going to erase it, and now it is how you roll up, like. So more like in this direction.
Yeah, and maybe that's because the guide field direction.
This I always say this is a kinetic signature of the electron precipitation along one branch of a separations. So this will be flux rope signature.
Okay.
It's not Helmholtz. It will be opposite.
Okay.
Okay. Well, and the other idea is like some people trying to use maybe the tail here have something, right? And cause the beading, and the signature is shown here.
Yeah.
I think, I'm not sure whether it's conclusive or not, but I think the issue probably is the scale size, right? Because it's very small thin ionosphere, and then need to map back to the tail region. If it's actually scale Helmholtz, probably cannot explain that. Maybe the scale size does not match. So it's really, when you see the aurora signature, you don't know exactly where it comes from. Yeah.
Let's thank our speakers. Sorry.
Okay.